All right, so before we start, just a little live visualization. This is the amount of personalization transactions per second that we do. Actually, it's all done through a service mesh developed here in IBM called Istio, which is part of Kubernetes. So this is for the team upstairs, just to let them show that we use the system. All right. So my name is Alon. I'm managing the release engineering group in Taboola. Before that, I built the Kubernetes platform for the company. So I've been in Taboola on and off. I've been going back and forth for 3 times. In this period, I'm with Taboola for 2 years. All right. So the agenda for today is what is Taboola, what is AI for Taboola, what needs to be done in terms of the mission, and how did we do it. Just a disclaimer, I'm not an AI person, I don't do math, I'm just a software engineer.
Not just, excuse me.
No.
You are a software engineer.
So what is Taboola? Taboola is the leading content delivery platform. So this means that we connect people to content. So if you all go to Ynet or CNN, or actually CNN not, but ESPN, Disney, MSN, LinkedIn, all of the recommendations, all of the recommendations, the advertisement, and the organic context is delivered through our system. So just the numbers. So we get 1.4 billion unique users a month. We reach 52% of all the desktops in the world, 550 billion recommendations per month. So we talked about 40 gigabyte data set. We get between 60 and 70 terabytes a day of data, and our data pipelines actually stream about half a peta because we analyze data more than once. So this is the amount of data that we need to work with. We can work with. Actually, it's good because we got all the data in the world. So basically, we use AI for most of the common cases that we need for us. It's deep scoring for articles. It's doing real-time recommendation or personalization for requests that we saw in the visualization. And we do a lot of fun things like we give publishers, especially news publishers, visibility to what's going on in the world live. So for example, if Trump tweets something and we know that it starts a ripple effect in the United States, we'll say our publishers, our websites like Bild in Germany say, hey, Trump did something, you should put it on your front page, it will get you clicks. Or, you know, this reporter brings you a lot of money, you should promote him in the page. So we give this live information to our publishers. So in terms of infrastructure, we got 7 data centers. We have 130 GPUs that are doing training. Our AI, which in an AI I mean both training and inference, we use 40K cores and 200 terabytes of RAM. It runs over 1,000 bare metal servers. We use Kubernetes, and the clusters consume 5,000 pods to do all this task. For the inference, we serve over 40K requests per second. We have more than 120 concurrent models every second, and we do a lot of A/B testing. So for example, we have our large models that serves different purposes. We have models for the Asian market. We have models for Microsoft. We have models for Europe, but we do a lot of A/B testing all the time. And the request latency must be less than 30 milliseconds in order for us to reply fast. So this is a very huge investment in infrastructure, in software, in people. We got our algorithm group is about 50 mathematicians. So this is a lot of money. Why do we do it? Actually, this should work. It's money. We do it for revenue. When we use personalization during a request, it increased our RPM by about 25%. So we get 25% more clicks when we personalize the response that we send back to the website that worked with us. So what's the mission? We have more than 120 models. We need to train them constantly because things change in the world constantly. So there are new articles, new pages, new data is flowing through our system. We need to train the models. Training job can take up to 12 hours per model. That depends on the model and depends on the data set. Rolling out the deployment can take time, although it's Kubernetes and it's very, very, very easy. By the way, I didn't ask, how many are you familiar with Kubernetes and with Airflow? Okay. We'll get to Airflow in the future. Deployment takes time because we got one model with 1,800 pods. So replacing them, there is pod warm-up. It takes 3 minutes to warm up a pod and know that it can reply in a timely manner because, we need to reply within 30 milliseconds. And the last part is building process. Like every machine learning pipeline takes a lot of steps. You need to prepare the data, you need to process the data, you need to train the model, you need to deploy. So it's a cumbersome task. Okay, so what did we do? So the first thing we do is we went to Jenkins because Jenkins is heavily used in Taboola. We all know Jenkins, it's battle tested, we know the pitfalls, it's a well-known infrastructure, but the problem is that it's in Chronos. So when you start an executor, it begins the training can take 12 hours, but if something happens in the middle, like we need to restart Jenkins, the executor fails, then we lost a lot of hours of training and we need to restart it. Another thing is that Jenkins pipelines are written in Groovy. Our algorithm team knows Python. So we need to do all the shifting of knowledge. And it turns out that we in release engineering had to build all the pipelines, maintain all the pipelines, and it was impossible eventually. And the last thing is that it was very hard to report errors and give the algorithm team, the algo team, what they needed to do in order to analyze errors during the process. Because, for example, training creates a lot of data, metadata in between. So so after we decided that Jenkins was not good enough, actually it did run on Jenkins for quite a lot of time, but we had a lot of problems. We decided to go to Airflow. Airflow is a scheduler developed by Airbnb, contributed to Apache. I think that it was July 15 when it was contributed. It's written for developers. Developers write their code in Python. So it was very hard for the algo team to shift to Airflow. They can maintain their pipeline, their scheduling. A few concepts that we'll follow with. The first one is DAG, is the graph. The graph is the workflow itself. So the user writes steps in Python that describes the graph. Then we have each step is called a task. We have the operator, which is the actual code that needs to be run. For example, I got an HTTP operator that performs an HTTP request. I can have a MySQL operator that query MySQL, HDFS, etc. So this is operators. And there are two main types of execution. The first one is local execution, where the scheduler just runs the task on the same hardware. And there is celery, which is celery, like the vegetable, which allows us to put in intermediate a queue, like RabbitMQ or Redis, that allows us to distribute the task into external workers. We'll show that in a second. Okay, so for example, I have a simple DAG. The DAG it should run daily, and it has 3 operators. Never mind what they do. Let's call them 1, 2, and 3. So on the first thing, I got the local execution, for example. So the Airflow scheduler will read the DAG from the disk. It will translate the Python into 3 tasks that you need to perform in a serial manner, 1, 2, and 3, and it will run it locally on the same machine. Obviously not scalable, problematic. You cannot have a lot of executors on the same machine. There is resource limitation on a machine. Although we use as part of our machine, you have 200 cores and 2 petabytes of RAM, 2 terabytes of RAM, sorry. I don't know, there is a 2 petabyte machine. 2 terabytes of RAM, it's still problematic. So here comes Celery. We'll put in a queue, and we'll have an Airflow worker, which can be anything, like a Kubernetes pod, a hardware, a physical machine, and then the worker will read tasks from the queue and will execute them on order. So that's still not good enough. For what? Because the worker workers are general purpose workers. So they need to be able to execute any type of task. So in order to do that, we need to upload all the Python libraries in advance to all the workers, right? And in addition, if I got a long running task like training, which takes 12 hours, I still have an executor that runs 12 hours to do the training. So it's not so scalable in terms of what we do. So there is an amazing article by Jessica Laughlin, which called We're All Using Airflow Wrong, which describe a way to work differently with Airflow, and we went with that. So the main difference is that we have our Celery here, and they say that let's externalize the workload. So we don't have a specific worker that does it all. Worker will actually only call an external resource. For example, in this case, it will call a pod in Kubernetes that will do the task, and then will reply the worker. So the workers are now very lean. They are not specialized. They just know to execute a container. And with parameters, the container knows what to do. So this looks very scalable, right? We got minimum, we might have a lot of workers, but all the workloads move to where it should be executed. Are you with me? It's okay? All right. So, but it didn't work for us. Why? Because in our case, we got like between 500 to 1,000 tasks in parallel with the single Airflow. So even if I put a quarter of a core for each worker, I still have to spend a lot of money, a lot of resources on the infrastructure itself, on the workers. I need to manage the queues. They need to be scalable. They need to be highly available. So even though the workers are very small and very efficient, and the work only done outside of them, they still consume a lot of resources which are useless. I have an executor who does nothing, who just waits for the pod to complete its execution, and then I'm wasting a lot of cores. So the problem is resource consumption. So what we decided to do, we decided, it's okay, that's the same, sorry. So just an example, this is our DAG. This is the graph of the training models. So you see the amount of tasks here, it's enormous. You cannot have them. We didn't want to spend the amount of, we didn't want to spend the resources on the workers themselves. So we decided to go async all the way. So instead of running, and this is a new paradigm for Airflow, which is not commonly used. So we decided to do async. So the executor is not waiting for for his workload to start, to end. What it does, it just run it locally, and the containers and the operator just ask, is my task started? If not, start it. Otherwise, exit. And then it will run again and say, are you running? Yes, I'm still running. So it will exit until the pod itself finishes, and then the operator will collect the load and the result, and send it back and ship it back to the next task. So what we did is we actually eliminated the resource consumption of the executors. They are all running locally, and what they do is just start, create the pod, and exit. And until it finishes, it just poll, in a polling manner. It will start, ask, is the pod finished? No? Okay, I'll wait another minute. If not, if it's finished, I'll collect the logs and move them to the next task. So this is what we did. What it enabled us is, first of all, move to a very simple architecture. We only have Airflow in local executions. We don't have the queues. We don't have the workers. We don't have anything complex. We reduce the cores. We only use 4 cores for each Airflow scheduler now. It allows us to create scheduler for each development team without having holding a massive infrastructure. Because if you use Celery and you have queues and you need to maintain RabbitMQ, it's resources, and you don't want to do that for different teams. That's why we managed to isolate workloads between teams. It allows us, for example, to restart Airflow. Airflow does not load plugins. Plugins are the operators. It does not load plugins on the fly. You need to restart Airflow. But because we work in an async way, I don't care if I restart it. Airflow will start, will read the DAG, will know it needs to execute a workflow. The operator will start, will ask the pod, are you running? He will say yes, and we'll return to the same position. So we can restart Airflow as many times as we want. And I said that we separated the Airflow schedulers for each workload, or for each team in our case. So it allows to simplify all the infrastructure that runs the training and the deployment process in a very simple manner. That's it. Questions?
Well, we'll keep the questions.